Assalamu alaikum students, to the online participants and the physical participants. Dr. Iqbal is trying to log in. Actually, he is currently in Lahore, so the class will be started in 5 to 7 minutes. Okay.
Disconnect. Yeah. Set disconnect.
Hello. Can you hear me?
Assalamu alaikum, sir.
Welcome, Salam.
Yes, sir, we can hear you.
I'm really sorry. I think there was something wrong in Zoom link. I was not able to connect with the audio and video. So, okay, everyone. Thank you very much. I am on the road again, traveling. This time I'm in Lahore.
I'll call you later.
Okay, so I hope you can hear me and you can see me as well, right? Can you hear me and see me?
Yes, yes, sir.
Okay, everyone. Okay, let me share my. Now tell me if you can see my slides.
Yes, sir.
Thank you very much. Thank you, everyone. And let us try that we resume of what we were discussing the last time. And I just want to take you back to what we were discussing very briefly, and then we move on to the new concept. My colleagues would actually then uh, explain all this to you a bit more in length. So this is what actually happened, that in the absence of magnetic field, applied magnetic field B naught, uh, these nuclear spins are randomly oriented, called degenerated. And once you place them in the magnetic field, depending on the spin quantum number, they can align themselves to various quantized spin states. For instance, for spin half nuclei, uh, there are two energy states. One is called aligned to the magnetic field, or the other is opposed to the magnetic field. And the one which are aligned to the magnetic field are in low energy states, and the nuclear spins which are opposed to the magnetic field are in high energy state. And we've also discussed that these are dipolar nuclei such as proton, carbon-13, nitrogen-15, and others, P31 and F19 and others. But there are many other nuclei which have more than two energy states, and they are called quadruple nuclei. They're often difficult to detect, but in many cases, you can detect them depending on their natural abundance as well as the applied magnetic field. We have discussed that this is a very, very important equation, that Larmor frequency, when you place them in the magnetic field, two things happen. They start precision, which is called Larmor frequency or precision frequency. And the other, as I explained, that they are divided into two energy states. Now, having said that, I also told you that the NMR spectroscopy is one and the only technique in which both energy states are populated. And I told you the reason, that the difference between the two energy states in terms of energy is so small that there is always a movement of nuclear spin up and down. And as a result of it, even in dipolar nuclei, the difference in population of two energy state is really very low. We have seen that you can move nuclear spin from low energy state to high energy state by the absorption of radio frequency. And the difference between the energy states are directly proportional to B naught. B naught is applied magnetic field, and remember I told you that the initial attempt to make this technique, which is inherently very insensitive, was to develop better and stronger magnets. So, initially permanent magnets, and after that electromagnets, and then finally superconducting magnets were developed. As a result of it, B naught was larger and larger, and when B naught was larger, then in that case, uh, the energy difference is higher. When energy difference is higher, then the population difference is relatively better. So the population difference between the low energy state and high energy state is called Boltzmann distribution axis. Why is called Boltzmann distribution axis? Boltzmann was an Austrian scientist, Ludwig Boltzmann, and it was in 18th century. It has nothing to do with NMR, but he was trying to explain. He was a mathematician and with a lot of experience in particle statistics, he was one who said, in low energy state systems, both energy states are populated. And he was talking about in the context of atoms and others. And he then mentioned that the difference between the two energy states is too little, that is just a small excess of population in low energy state. And that is called Boltzmann distribution axis. And I told you that, roughly about if you have 100,000 nucleus spin in low energy state, there are 100,001 uh, population in the high energy state. Is only one. So in a million is about 10 to 13. So it's a very, very low energy population difference. And also, this is a very important equation, again shown to you, that Larmor frequency is also dependent on magnetic field. The stronger the magnetic field, more this so-called circular angular frequency of nucleus spin would be. So not only that magnetic field affect the energy difference, but also the precision frequency. Both are related. And this is the reason that many development initially in NMR spectroscopy were based on developing a stronger magnetic field. Remember that I showed you this equation number of times, and I told you that this equation is the key to understand NMR spectroscopy in many, many contexts. For example, Larmor frequency is what you're trying to detect. I told you that magnetic gyric ratio or gyromagnetic ratio, which is shown here, delta, is specific for every element. It's experimentally measured, but you can calculate that also. But it is experimentally measured. And I told you that magnetic gyric ratio is a very important concept. And that is, these nuclear spins of different elements are magnets, tiny little magnets. And B naught is large, ever-present applied magnetic field or magnetic field flex density, a very large magnet. And every element would have a different susceptibility towards large magnet. And I gave you an analogy that if you have a permanent magnet and if you have coins and pins of different metals, not all of them will be attracted to this permanent magnet with the same intensity. And every metal would have a different reaction towards the magnetic field also. So carbon, nitrogen, hydrogen, oxygen, phosphorus, sulfur, all of them, chlorine, bromine, they would have different magnetic gyric ratio. As a result of it, this Larmor frequency is going to be very different for different elements, right? That's it. And this is the reason that you can selectively detect one element in the presence of the other element. So selectivity is so high that if you have a molecule in which you have 4 different elements, for example, carbon, hydrogen, oxygen, and nitrogen, which are very, very common in organic chemistry, then you would be able to record NMR spectra of all 4 of them separately. So you would be able to have NMR of proton, which is your hydrogen. You would be able to have NMR of carbon-13. You would be able to have separate NMR of oxygen, and you would be able to have NMR of nitrogen. What you need to do, magnetic field is constant. For the machine is superconducting magnet, the machines which you have seen in our NMR laboratory, each machine has a constant magnetic field. And if you wish to detect one element, you just need to focus on the Larmor frequency in which that particular element resonate. So you can just tune your alarm frequency and they can detect it. And now alarm frequency is actually, I told you that in quantum physics, alarm frequency is measured only by resonance frequency or radio frequency, because that is to be exactly matched. So alarm frequency of carbons of different kinds has to match with the radio frequency which you apply, and radio frequency would tell you, will give you flexibility of detecting one element in the presence of others. So, as I said, that Larmor frequency is not only dependent on B naught, but also dependent on magnetic gyric ratio. As a result of it, you can select matching radio frequency, and you can select one element in the presence of others. Very, very important concept in NMR spectroscopy. Okay. Similarly, within one element, for instance, you are just detecting proton hydrogen in your sample. This Lyman frequencies are slightly different from each other depending on B effective. Remember, I told you that electrons have a very important role to play. They shield or deshield. And this shielding by the electrons or deshielding of the electrons is which affects applied magnetic field for individual proton, because B naught is same for all elements or all hydrogens, but B effective is what is the result of it when electrons own magnetic field minus B naught, which gives you B effective. As a result of it, Larmor frequency, for instance, in ethanol, alcohol, is going to be 3 different Larmor frequencies, for CH3, CH2, and OH. Because the B effective for CH3 is different. CH2 is different, OH is different. CH3 has lots of electrons. CH2 has relatively less electron because it is directly connected to electronegative atom, oxygen. And then, of course, proton is directly connected to oxygen. And as a result of it, the electrons shielding in all 3 types of protons are different. And as a result of it, the Larmor frequency for them would be different. And when you will start sweeping your radio frequency, when it matches with CH3, you get the absorption. When it matches with CH2, you get the absorption. And then when it matches with the OH proton, Larmor frequency, you get the absorption, and you get 3 peaks, because 3 peaks represent 3 absorptions of radio frequency, and that is that there are 3 Larmor frequencies of these protons. So it's a very, very important concept. While magnetic gyric ratio defined which element you're detecting, B effective is defining within the element which proton you're detecting or which carbon you're detecting. Again, let me repeat it. Magnetic gyric ratio defines which element you can detect. B naught, which is B effective, will define that within that element, which proton you are detecting, because B effective is different for different types of protons, even within a particular molecule, because of their microelectronic environment. And let me show you this table, a very, very important table. So this is proton, this is deuterium, this is carbon-13, this is F19, okay? Proton is 99.98% abundant. This is the dominant isotope of hydrogen. Deuterium is naturally abundant 0.01%, very, very little. This is called heavy water if you have a deuterium water, okay? Carbon-13 is about 1.1%. Fluorine is 100% abundant. And then, of course, many, many other elements such as nitrogen, which is 0.036, and oxygen, which is even less. And so natural abundance. So don't worry about that. Natural abundance is just shown for your understanding that the more the element would be abundant, you would get a stronger signal. You know, because you should naturally have more population. Now, this is your NMR spectrometer. For instance, if you have NMR spectrometer with 1 Tesla magnetic field, okay, remember Tesla and Gauss, both are the unit used for the measurement of magnetic field. So magnet is about 10,000 Gauss, which is equivalent to 1 Tesla. So forget it because Tesla is the standard, international standard unit used for magnet. Gauss is generally used for weaker forces, and it's just Tesla is much larger, Gauss is much smaller, 1,000, 10,000 Gauss equivalent to 1 Tesla. Okay, just forgot it. So 1 Tesla and the frequency, Larmor frequency, and of course, radio frequency, which need to match, is 42.6. Okay, remember that for hydrogen 1, the magnetic Garrick ratio is constant, 267. Now, this is this equation in action. Okay, if you have a machine, superconducting magnet, which is a 1.41 Tesla, the protons will resonate with 60 megahertz. Okay, so precision frequency, the average precision frequency of all the protons would be about 60 megahertz. When a stronger magnet, 2.37 Tesla, the proton will resonate with an average angular velocity or Larmor frequency of 100 megahertz. Okay. When the magnet is 7.05, the frequency is going to be 300 megahertz. So remember, for proton, the magnetic field is same, right? Magnetic Garrick ratio is same. We are just talking about the magnetic field. Okay, so you see that you increase the magnetic field, strengthen the magnetic field, you have a stronger magnetic field. You have NMR spectrometer with a stronger magnetic field. You would have faster Larmor frequency and radio frequency absorption. So this is for proton. Let's take the example of very important nucleus, which is C13. It's only 0.1% abundant. It means that, it's always very sensitive because you're talking about only 1% of carbon in your molecule, which are detectable. In its magnetic Garrick ratio is 67, about 1/4 of it, right? So two different damping factors, two important weaknesses. One is natural abundance is less, Second is that magnetic Garrick ratio is even much weaker. It means that, as compared to proton, this is a weaker magnet. Now, at the 1 Tesla machine, the Larmor frequency and radio frequency absorption in average is about 10.7 megahertz. At a 2.35 NMR Tesla NMR spectrometer, this is 25 megahertz. And for 7.05 Tesla machine, it is 75 megahertz. So see, this one, even with the same NMR spectrometer, the frequency are different because they have a different Garrick magnetic ratio. Here, what I would like to tell you that NMR machines are defined on the basis of proton megahertz, So when Humera and Sumera will tell you this is a 300 megahertz machine, or this is 500 or 400 or 600 or 800, they are trying to tell you that these are stronger magnet, and the frequency, these machines are actually defined conventionally. It's not a very correct convention, to be honest, but since NMR was developed largely initially for proton, machines are defined on the basis of their frequency for protons. So 300, 400, 500, 600, it means that, B naught are stronger and stronger and stronger. This is what I'm going to tell you. You also wish to understand that and appreciate that proton and carbon-13 are so different from each other. Proton is nearly 100% abundant. Carbon-13 is only 1% abundant, so it's always very, very weak. On top of it, it is a poor magnet as compared to proton. And as a result, the Larmor frequency is much weaker. The population difference is very low, and it was a huge undertaking of detecting carbon-13 in natural abundance. And, people were very, very eager to detect carbon because all bioorganic molecules are made of carbon. And their interest in carbon was so enormous that they keep developing larger and larger magnets so they can detect carbon-13 in natural abundance. When I say natural abundance, means without any enrichment, just what exists, 1.1%, which exists in your molecule, which you isolate or synthesize. Okay, so showing this table was to demonstrate you that depending on magnetic Garrick ratio, the precision frequency for different elements are different. At the same time, it is also dependent on magnetic field. Stronger the magnetic field, stronger the precision frequency, stronger the absorption of radio frequency. And that is the reason that people could not do anything with gyromagnetic ratio. You cannot change gyromagnetic ratio, but you can change magnetic field. You can have better magnet, and the key advantage of modern physics was that people were able to develop stronger and stronger magnets. And I told you that now 1.3 or 1.2 gigahertz, 1200 megahertz machines are available. When I say 1200 megahertz, this is the frequency of proton. NMR machines are defined on the basis of the frequency of proton. Why they do that, I have no idea. I think it's more historical than anything else, because you can see that for carbon-13 is just 1/4. So people measure carbon-13 all the time, but machines are defined on the basis of the frequency which they get out of proton element. Now, That is what we would need to know. What are Larmor frequencies? What factors on which Larmor frequencies are dependent? We have discussed this earlier. This is what you see. And you see that, is axial moment and precision mechanism. But this is not the only, I mean, you don't have one nuclear spin, you have millions and trillions of nuclear spin. So in fact, both up and down, in dipolar case, spin half nuclei, the population exists, and these magnets, thousands of millions of these magnets are resonating up and down. The difference between them is just very little, and that we would discuss later. And of course, if you wish to record this Larmor frequency, then you need to perpendicular to this, you need to give radio frequency by a small little radio, which is called radio frequency oscillator. And as soon as the radio frequency match with Larmor frequency, you see an absorption, a signal. And if you have three different types of precision frequencies, Larmor frequencies, then you would have three different type of absorptions. So you have three signals, and you record the NMR. Now I want to show you historically what the NMR look like. NMR are quite different now. The concept of NMR is different as well. In all spectroscopic techniques, the concept has not been changed. Equipment have been improved, but concepts remain the same in UV, IR, X-ray. No matter what you do, the machines essentially, the theory remain the same. Electronic transition, burning stretching, and all that. Scattering by electrons in X-ray. The concept of the first machine, which was developed 100 years ago and even today, remain the same. NMR has changed substantially in terms of its theoretical and foundational principles. So, for instance, this was the earliest NMR when people placed a sample under the permanent magnet, and permanent magnet cannot be more stronger than about 50, 60 or something of megahertz. I mean, roughly about quarter of a Tesla or half a Tesla or something like this. And so you place your sample. Your sample is there in this tube, NMR tube. This is the applied magnetic field, and Larmor frequency, etc., are taking place in this tube, and then you give a radio frequency. Radio frequency is absorbed, detected. Absorption is detected, and you get the spectrum. So, for instance, if you have like 10 different types of proton, then you get 10 different types of 10 different signals, right? Now magnets are superconducting, right? So magnets look very different, and we will see that also radio frequency is essentially the same. Detectors are different now because detectors do not really detect absorption of radio frequency, they detect something else. The machines which were initially developed were detectors designed to detect the absorption of radio frequency. And of course, you don't record NMR directly. You record free induction decay, and I'll tell you what. So this is the conventional 60 megahertz, a Tesla machine or something. And, so this is your NMR tube magnet of roughly 1.4 Tesla, and Radio frequency was given, radio frequency was detected, and you were recording it. There was a serious issue in that, It's called conventional NMR or continuous wave NMR. And the issue was that, if you have a simple molecule like ethanol, you need to sweep. You need to increase the radio frequency slowly so it matches, you get one peak, then you increase, it matches, you get the second peak, and you increase the radio frequency, it matches with the third, you get a third peak, So you're sweeping. This is the term which is used in NMR spectroscopy is called sweeping, radio frequency sweeping. Radio sweeping is like, you sweep. जैसे झाड़ू देना होता है ना, radio frequency sweeping. So radio frequency was initially increasing, and this was a very inefficient procedure, So it was a torture. So for instance, this is a electromagnet. Somewhere in 60s and 70s, I've seen this machine myself. I didn't really use it. I was lucky to use superconducting magnet, but I've seen that one in Jamshoro, where we had the first NMR, which was a permanent magnet, and we used to have a very dear friend called Iqbal Khanzada, who was maintaining this machine. And can you believe it that in universities of Sindh in 70s and 80s, they were using NMR. And these were permanent, these are electromagnetic. So you have your sample inside. Okay, and this is a chart. This is essentially a paper scrolling. And there are so many knobs here. And these knobs were largely sweeping radio frequency, which you can see on this particular meter. So let's say if you have a molecule with 10 different protons, 10 different types of protons, you stand here, and this is the reason they were developed like standing, because you really need to stand and sweep, and you're slowly sweeping the radio frequency. It's called continuous wave, and slowly and gradually each proton was detected. So for one proton NMR spectrum, it takes about 2 hours or 3 hours, sometimes the whole day. And if you are not careful enough, and if you are sweeping the radio frequency fast, then you miss it, because it's just goes in back and all that, and you just have a distorted NMR. Extremely slow technique and insensitive technique, because it's time inefficient. It takes so much time. At that time, people were using a very conventional technique that they used to record many NMR spectrum and try to improve signal to noise ratio, but it was not very efficient technique, and you were literally increasing scanning from downfield to upfield. You were increasing either the radio frequency or B naught. B naught is not so easy to magnetic field is not easy to sweep. Radio frequency was easier to sweep, so you get that, and eventually continuous wave NMR spectroscopy until 60s was the method which people were using. You cannot really, it's insensitive technique, not suitable for large molecules. Biomolecules, noise were really high because, signal to noise ratio is called sensitivity. Remember that NMR machine is a very weak, is NMR machine is trying to detect weak signals. And there's so much of noise, Noise comes from slight changes in electromagnetic, B naught, slight change. Somebody passed through a noise or temperature difference of metal or something like that, you get a lot of noise. So noise and signal compete. If you have noise which is high and signal is weak, you cannot detect signal. Noise has to be less, signal has to be stronger. It's called signal to noise ratio. Noise are random, signals are constant. Signals always come on one place. Noises are different because noises are because of multiple reasons, and that can occur at different interval of time. So signal to noise ratio in continuous wave method was not really good, and it was a very slow, inefficient technique, which make this technique very, very inefficient. And at that point of time, people start thinking of what we can do literally. So, for instance, if you have a molecule like this, 1, 2, 3 different types of protons, although, you would learn that even this benzyl group, this phenyl group, have 3 different types of protons, but in continuous wave, they were coming as a one signal because sensitivity and resolution was very low. So, you place your sample of this molecule, and alarm frequencies are established, radio frequencies are absorbed. You get these 3 signals. Now, essentially, you get 3 different types of information. Integration will tell you how many types of protons, CH3, 3 stronger signal. I mean, more integration, CH2, relatively smaller, and these 5 protons much larger than 3. So, and this chemical shift, second information that tells you about what kind of environment they have. So, for instance, in case of phenyl, this is a very de-shielded system because of magnetic anisotropy, which we will discuss later. And you see these signals coming in the downfield region, and they are coming in the upfield regions. Metal is the strongest, has more electrons than any other type of proton in this molecule. CH2 is also between carbonyl and phenyl. So this is more downfield, and you get signal here. So that tells you their micro electronic environment, and that help you to elucidate the structure of the molecule. You also get one more information, and that is the splitting. In this case, of course, there is no splitting. I expect the splitting to take place here, but it's not. Is it actually a low resolution NMR spectrum, to be honest, and therefore I expect that 1, 2, 3 different types of proton appear in it, but continuous wave was not a very ideal technique to detect, to see resolution in a higher way. And so this is what NMR spectrum should give you. Peak position, chemical shift, tells you about the electronic environment, help you to develop structure. Peak splitting, coupling constant, tell you about the neighboring nuclei, which help them to split. Peak intensity gives you how many that type of protons present. Peak shape also gives you some information because often exchangeable OHs, NHs appeared broad signal. So a lot of information which you get from NMR, and there is no other technique which gives you so much information than NMR. And that is the reason why NMR is just fascinating technique. Then people thought, it's just absolutely not on that we constantly spend a lot of time to record weak NMR. And even that NMR was not suitable, sensitive enough for large molecules where you have many, many different types of protons. And for that sake, for proteins, because proteins are absolutely not suitable for this kind of NMR instrumentation, which is called continuous wave or conventional wave NMR spectroscopy. And back in 1949, immediately after the development of NMR spectroscopy, someone, his name was Edward Hahn in US, he was puzzled. He said, why we need to record, why we need to excite one proton by one proton by one proton. He said, why don't we just excite them all together? Why not we just give them a radio frequency which is which all protons in the molecule absorb and go back and record instead of absorption, relaxation, release of energy when they achieve thermal equilibrium. So back in 1949, and nobody actually gave him much of an attention at that time until a very eminent scientist called Richard Ernst, who received the Nobel Prize on his first development of pulse NMR spectroscopy with Fourier transformation, made it practically possible back in 1970s to what Hahn was saying in 1949. So sometimes this seminal excellent thinking are not really noticed by the scientific community. Richard Ernst received Nobel Prize. He unfortunately died some years ago from brain cancer, and he used to show the MRI of his brain. I still remember his last visit to Pakistan, and then we met him in Jordan, and he was showing the NMR of his own MRI of his own brain and the cancer which he had in his brain. He was still traveling, and he was a fascinating person. He wrote forward for our book also. Richard Ernst came to Pakistan at least 3 times, and a wonderful soul and a great scientist. But you see, what I'm trying to say, that he was the one who was able to apply that concept of Edward Hahn some 20 years ago. So what see modern NMR look like? These were NMR machine of the past, right? This was in 1960s when these machines were in fashion, quite expensive, and even at that time, also continuous wave NMR. New machines look like this, which you have seen in your institution. So 800 megahertz NMR machine, which we procured. I remember I was sitting in France with all these people of Ruka, and in a restaurant in the hotel lobby. I was trying to convince, and I did convince that along with 800 megahertz, they will, of course, we got half a price of what people were buying it from the other part of the world. Also, at the same time, I was able to convince them. They've flown from Switzerland to meet me in France, in Paris. and I was able to convince that, this machine is state of the art at that time. Now, much stronger machines are available. I said, why don't you just change the consoles of remaining 5 machines? At that time, we had 600 and 400 machine. 300, we didn't really change the console at that time. So everything was done. This new machines was purchased, consoles were changed, modernized the entire NMR battery. We call it, the NMR park. And there was the cheapest in the world ever, because we were able to convince them that this part of the world in Eastern Hemisphere or southern global South, this is the most powerful NMR park. And if you wish to bring people to show what NMR can do, this is the place you bring them, instead of bringing them to Switzerland, Geneva, or France. And we have this fascinating machine working on. So this is how modern NMR machine look like. Very unlike of old machines. Everything is just hidden. This is the computer, so it's just a computer, and this is the magnet, and that's it. And then you get a screen on which you see the spectrum. So this is how modern NMR look like. And the reason why, before introducing pulse NMR spectroscopy, I'm showing you this because this could have not been possible without much advancement in this instrumentation. Okay, so superconducting magnet are made of very exotic metals such as niobium or niobium's tin complexes and others. A lot of very rare metals which constitute these magnets, often in a cylinder. They need to be at the coldest temperature you can achieve by liquid helium. Nothing is colder than this, minus 270 Kelvin. Remember, the room temperature is 298 Kelvin plus, and minus 278 Kelvin is close to absolute zero, in terms of minus. So this is the coldest thing. If you place this magnet in liquid helium and give this magnet electricity only for a few seconds, this electricity, these electrons as moving in this cable remain there. Conductance is close to 100% and resistance is close to 0%. And that is the reason called superconducting, because now you disconnect the electricity, this remain a magnet until you keep this temperature of minus 270 Kelvin. Okay. And in order to protect liquid helium from the external temperature, you have a liquid nitrogen outside. So these are two rivers, one inside the other. The inside one has a magnet and helium, outside one has a liquid nitrogen. So you can see that you fill liquid nitrogen from here and liquid helium from here. Okay, and this is the conducting magnet. You place your sample here. There is air which is going in. Air bring that sample here. This is your sample. And now the sample is sitting in between the magnet. It is on room temperature. Liquid helium is minus 270 Kelvin. It is just a centimeter away from liquid helium, and the temperature difference is just huge. So this kind of an insulation required. So it's called Bohr. And you have seen this probe, which is inside probe is inserted from here down there, and the sample is inside the probe. That probe provides an insulation between minus 270 Kelvin and ambient room temperature. So this is the kind of setup you need. Closer look. So this is liquid helium, liquid nitrogen, your magnet, your sample, radio frequency oscillator, detector, and instead of absorption, you record free induction decay. That is the theoretical and conceptual difference. Do they have a class today, Hina? Are they
No,
available?
they don't have a class.
They have a class?
No, they don't have a class. Our class will be till 12:30. We have time till 12:30.
Okay. Okay, so so this is the kind of machine you have, and I'm confident that my colleagues will take you again to NMR lab, and they'll show you what NMR. I mean, of course, they can't show you inside what is happening in the magnetic jacket or this dimmer, but they can still show you the probes, which is this is the probes, and you know how sample goes inside. So when they place sample goes in the airbag inside and sit nicely in the magnet where it experiences the B naught. If you're detecting proton, different precision frequencies, and now you have an option, either you go for an old conventional way of giving radio frequency and recording the absorption, but that is not the one which you use. It's just for historical purpose and to have some understanding of NMR at the concept level. So this is what actually is very, very important. This is low energy state. Assume that this is the V naught on this direction, Z, negative Z. So these are your nucleus spins moving with their precision frequencies. These are the nucleus spin. They're moving in their own precision frequencies. This is the high energy state. This is a low energy state. And both energy states are populated. And I told you that this is because of thermal equilibrium. The energy difference between two energy states is so tiny that Boltzmann says long time ago that when such system exists, the excess is very little. So assume that you have 110 nucleus spin and low energy state, and you have about 100, and just an arbitrary number, 100 in the high energy state. Remember, these are tiny magnets precessing around the B naught. And magnets have the direction and magnitude, right? Remember, these are vector quantities, and vectors are cancelled. So 100 vectors from above, 100 vectors from down would be cancelled. What remain is the axis population, about 10. And since they are all oriented towards one direction, you can represent them by bulk vector. This is a simple vector statistics. You know vector what. So vectors have direction and magnitude. So the magnitude is same, the direction is different, they cancel each other, they're gone from your state of mind. What remain is an axis, distribution axis, okay? डिस्ट्रीब्यूशन एक्सेस, दोनों एनर्जी स्टेट के दरमियान जो पॉपुलेशन का फर्क है वो सिर्फ रह गया. एंड दीज वेक्टर्स which are representing, let's say about 10 of them are in the same direction, therefore they can be represented by a bulk magnetization vector, which is also called net magnetization, because this is the net difference between two energy state. And this is denoted by M naught, denoted by NMR, denoted by M naught. Okay, so this is the magnetization vector. And believe me that I'm not really going to talk about this anymore. For me now, this is what I would explain to you all the time. And this is my bulk magnetization vector or net magnetization vector, which I would use always, because this is what I intend to show you in order to have a more pictorial understanding of NMR spectroscopy in terms of its modern concepts. So let me explain to you again the difference between low energy state. This is B naught direction. And the high energy state is little tiny. Vectors are canceling each other, and only the net difference is represented by a bulk magnetization vector. Okay, this is for understanding only. Kindly remember that in the physical world, nothing is canceling each other. It's just for only understanding that we know this tiny difference between the population of low energy state and high energy state is the one on which entire NMR theory is based, because that is the population, excess population, which will absorb radio frequency. The net absorption of radio frequency will be only by M naught. Okay, so M naught is the one which is in the direction of Z, and now this is called vector. NMR spectroscopy, most of it, not all of it, can be understood by a vector diagram. It's called pictorial vector diagram, and it's called bulk magnetization vector. Now, what Hans said in 1949 in a very small paper which was published in a very weak journal, he said instead of sweeping the radio frequency, if we give a radio frequency pulse, and he used the word pulse, and then of course it is now conventionally used in radio frequency domain all the time, but pulse comes from pulse of your hand, pulse. So if you try to feel pulse in your hand, it's just one after the other. And why he used pulse, I'll tell you later. But this pulse is a strong burst of radio frequency range that all the precision frequencies, all kind of proton, in case of proton, absorb and excite. Okay, so instead of absorbing and exciting one after the other, he gave the concept of a pulse, that you give a strong radio frequency, everything excites, and everything goes down. I'm sure that he was sick and tired of standing and recording this conventional NMR, and he was wondering why I need to, sweep this radio frequency. Why don't I just excite them all together and then record the relaxation energy? This was his concept, which was later changed also. I mean, pulse remain a good concept, but relaxation or excitation in terms of radio frequency wasn't really stood the time of the test of the time, and this concept has become redundant for at least 2 decades. And only when Richard Nance back in late 60s and early 70s, he developed this concept. So the pulse is radio frequency It means turning on the radio frequency for a small time period and then switching it off. Okay. This radio frequency pulse excite all nuclear spin at the same time instead of this conventional or continuous NMR spectroscopy in which everything was excited one after the other. Okay. When all nuclear spins are excited, then you can do different things. Okay. But pulse NMR spectroscopy has changed the entire face of NMR spectroscopy for good. Number one, that you don't need to spend time. You just give radio frequency pulse, excite them, record the relaxation. They go back to thermal equilibrium. Remember, thermal equilibrium is a stable state in which there is no exchange of energy taking place. It is an equilibrium state. It means that bulk magnetization vector or net magnetization goes back to the Z. And you keep doing it, like pulse. Pulse continue till our last breath. So he said, keep doing it, give pulse, record relaxation one after the one after. So pulse, give pulse, excite them together, record their relaxation. And by doing this, instead of spending hours, you can record many NMR spectrum in few minutes. You just excite them, wait for a while, relaxation take place, it goes back to the thermal equilibrium, give another pulse, record another relaxation spectrum, give another pulse, record excitation, record relaxation, and you keep doing it. So even today, the NMR which you get are about 32 skein, Humera, or 64?
Yes, sir, 32 scans.
Okay, so there are 32 times they are giving pulse and recording the relaxation. Okay, that is just so phenomenal, it was just so absolutely phenomenal. The people that at that time didn't really understood what to do with that relaxation spectrum because that was a bottleneck. So, later Richard Ernst combined this concept with Fourier transformation. And that has improved sensitivity of many-fold. This was a conceptual change, this sensitivity was changed by developing a sequence, not by developing larger magnet and investing lots of money. It was a conceptual change in which, scientists were able to develop a technique through which signal to noise ratio can be improved. Now, how signal to noise ratio improved? I told you noise are random and signal are always at one place. So if you're recording 32 spectrum, the signal will reinforce and noise will cancel. Understood? Because signals will always come at one same place, noises would be in random, therefore they become part of the baseline. So you buy a pulse NMR spectroscopy, signal to noise ratio was improved, sensitivity was improved without investing money in developing large magnets. This was the concept of it. And of course, you can give radio frequency pulse at different interval. Therefore, idea of applying a sequence of pulses, such as for proton NMR, you get 32 pulses, but you get thousands of pulses. When people are recording C13 in natural abundance, they give several hundred pulses. So they get better signal to noise ratio. And it becomes then possible of recording a decent spectrum of C13 in natural abundance because you change the concept, You're now recording not one, but hundreds of spectrum, And when you record hundreds of spectrum and accumulate them, you accumulate all this data one after the other, combine them together, you get a better signal to noise ratio. So the idea of applying a sequence of pulses is of central importance to all NMR experiments now. Today, no continuous wave spectrum. It just was the past, which has really gone by. So Richard Dawes got a Nobel Prize in 1991 on his discovery of pulse Fourier transformation. What are the pulses? Pulses are radio frequency burst. Pulse power, define which nucleus you want to detect. So if you wish to detect C13, your radio frequency pulses has to be tuned to the average precision frequency of C13. If you wish to record proton, your pulse has to be, radio frequency pulse has to be tuned for proton and so on for oxygen, nitrogen, phosphorus, or whatever. Pulse power, decide which nucleus you are detecting. Okay? Pulse power. So C13, different pulse power. Proton, different pulse power. Pulse width, even within the same element, now you have the capacity. And again, not only that you can detect elements, different elements separately without interference of the other, but also within the same element, you can also, even in ethanol, you can selectively irradiate or excite one type of proton. It's called pulse width. Okay. And this you would see when we will move on to a bit more complex experiment. As pulse duration, now this bulk magnetization vector, if you give 90 pulse, they come on XY plane. So it means that you give a duration of a pulse which bring this magnetization vector on XY plane. Very different concept, because in absorption, everything was going in negative Z. If you give 180 pulse, it comes to negative Z. So pulse duration define where your magnetization vector would be. Okay. So pulse power, define which nucleus you are detecting. Pulse width, don't worry about it. Even within the same elements, you can select one in the presence of the other, and pulse duration where you wish to bring. So you have this tremendous capacity in NMR spectroscopy to bring this magnetization vector M0 to any place in this three-dimensional XY Cartesian dimensional. So you can bring them to XY, you can bring to minus XY, bring it to minus Z, you can bring it to Y, you can bring it to minus Y, you can bring it to all different. So it's called longitudinal, and this is called transverse, So you can bring this magnetization longitudinal to transverse. And that is the most beautiful thing happen in NMR spectroscopy. And so nucleus spin M0, radio frequency pulse B1, which you are giving perpendicular to the system of M0, if you give a 90 pulse, that comes here. If you give a minus 80 pulse, this is pulse duration, this comes here. Okay, so you have this tremendous flexibility of placing this magnetization vector, which is representing net magnetization, anywhere in this three-dimensional Cartesian. So this is called right-hand thumb rule. And my colleagues would actually explain to you. First, they will explain to you pulse bit more. and then they will explain to you how this m naught can be. So if you're giving it from x, they move to this direction, means y. If you're giving this radio frequency pulse from minus x direction, they come to minus y. If you're giving it from the y, they comes to minus x. So this right hand thumb rule, thumb represent the direction of magnetic field, radio frequency, fingers representing m naught, and you turn light. You don't do that with the left hand, you do it only with the right hand. Okay. So if it is from the x, they will come from y. Now, why you would do that on the face of the earth? Why would you bother yourself of having pulses of this nature? Because your detector is now placed in modern NMR spectrum on XY plane also. And you want to see this magnetization vector comes to XY plane, going back to thermal equilibrium, this dancing of precision on XY plane, which reverse like a reverse umbrella, go back to there, like in this, from XY plane to Z is recorded, and it's called free induction decay. At this point, I would like to stop and let my colleagues explain to you this phenomena, inshallah. We're meeting on 23rd morning, inshallah, and then on Saturday in person before I travel to Brazil, inshallah. Okay, everyone. Thank you very much. If you have any question, please ask to my competent colleagues and they will give you excellent answer, inshallah. Okay.
Okay, sir. Thank you, sir. Allah Hafiz.
Thank you.
If no, then we can meet in next class, inshallah. Okay.
Monday?
No. On Saturday. Next class will be on Saturday. Yeah.